Mathematical modeling essentially is all about expressing real life problems into mathematical problems. Because in the real life, there are so many problems that can be solved. The word model simply means mimicking of real life situation. And there are different ways of mimicking real life situation. Like for example, when a tailor wants to sew a clothes, the first thing a tailor does is to design the clothes by drawing the picture of the clothes. So that picture is representing the style or the clothes the tailor wants to show. So that picture we can say is a model. In the past, in those days when camera was not yet invented, so people like kings normally make sculpture of themselves or ask somebody to draw the picture or painting about the person. And whenever you see the painting, it's a direct resemblance of the person. So therefore, model is a resemblance of what happened in real life. So for that reason, in mathematical modeling, what we are trying to do is to mimic what is in the real life by abstracting that thing in real life, putting it in mathematical form, and use our knowledge of mathematics to solve the problem. And after solving it, we interpret the problem from real life perspective. So that was what we do in modeling. And that's why we use the word mathematical modeling, because we are looking at the concept of modeling from mathematical perspective. Because every discipline have what they call model. In architecture, they have architectural model, because that model is talking about those artifacts which they normally glue together, and then which will show the representation of the structure, which at the end of the day, when the building is constructed, it will look exactly like that miniature they always produce. But here, mathematical modeling, we are talking about representing real life from mathematical perspective. Then after we, first of all, we conceive the idea of the problem we want to solve in real life. And then we now represent that real life problem with mathematics, whether using of equations, whether use of functions, whether use of some kind of mathematical structure to represent it. Just like Professor Trump was talking about machine learning vector. Such type of vector, which is mathematical representation, is what we call model. So next, after we must have formulate the problem in mathematical form, our next thing is to think of how are we going to solve that mathematical problem that we have solved. The mathematical problems can come from differential equation, which means that we must use our knowledge of differential equation to solve that problem. The problem can come from operation research. We must use our knowledge of operation research to solve it. The problem can come from control theory. We are going to use knowledge of control theory to solve it. It may come from algebra, so we must use knowledge of algebra to solve it. Then after that, the result we get, we have to interpret it back in real life form so that it will make meaning. Then mathematical modeling, the ultimate purpose of modeling actually is to make prediction, because we want to predict about some things we don't know. In real life, it is usually very dangerous to experiment with situation. For example, in a laboratory, for example, if you have to be mixing chemicals together, sometimes it can lead to explosion. So the best way of, first of all, experimenting with those things is to, first of all, design a model and see what will happen if social chemicals are mixed together. From our knowledge of chemistry, then we can know what will happen, instead of experimenting directly with it. And the same, like in a nuclear reaction, we cannot just go ahead and experiment reaction in nuclear. First, we must model it and test to see whether it will give us result, because such things are very dangerous to operate with directly. That is where modeling comes in. Other things again is that some things are very expensive to experiment or to use direct. So what we do is to design model and test the model before we go into prototyping, where the prototype will be developed. And at the end, we know the prototype, when we design it, model will tell us under what condition can you operate those things before you can use it. Another importance of modeling is a cost effective. As I told you, if, for example, you want to perform experiment, you have to spend a lot of money. You have to wait until the end of the experiment before you can make any decision on it. But with the model, you don't need to spend money. All you need to do to design the model and make sure that the model it has the desired property that you need. And then the result you get out of it, you can use it for decision making, so long as the model is very good. So therefore, modeling process save cost and it save time. Whenever we need to take urgent decision, the best thing to do, best knowledge you do is modeling rather than going for experiments. So there are several processes you have to take in modeling. And this process is common to any problem you want to solve, so long as you are using modeling. First step is you have to abstract that real life problem. First of all, conceive what is the real life problem you want to solve. Then you have to think of how you can use mathematics to represent some variables that describe that problem in real life. So in that context, we are talking about, we are formulating the model. So that model is simply simple mathematical structure that represent real life. Next, you have to solve it. Here, most of the session is talking about techniques. So techniques here is talking about when you formulate the model, from which area of mathematics you have formulated it, and what are the best possible method or the available method you can use to solve them. We are going to see many of them as we go ahead. Then next, you have to solve the model equation. For example, if I represent real life problem, like in epidemiology, I'm using differential equations to represent it. I should be able to solve that differential equation. I should be able to make sure that that differential equation satisfies all the necessary conditions, which means using theory of existence of solution to be able to test, to check that the model actually has solution. Because if the solution is what we use in making prediction. So if it does not have solution, then there's no need. Such model is as good as a useless model. So we have to solve it and go into what is called empiric verification. Empiric verification simply means from the initial condition you are given, you have to make sure that the model actually satisfies the initial condition. And if it satisfies it, then you should be able to find out under what condition can you use the model, because before you go into prediction. So here is prediction, because the ultimate purpose of model is prediction and control. Why do we need model? Actually, it's for purpose of prediction, to know about the future from the present. We can also use model to know about the past from present. For example, you can hear scientists talking about the temperature of Earth about 100 years ago was so. Of course, nobody went to, go to 100 years back to really know what it is. We can only arrive at that conclusion through the knowledge of models. You can talk about the temperature of Earth maybe 5,000 years ago, and that is through knowledge of model. When you iterate backward, you can tell what has happened when the Earth, most of the place, the temperature was very full of ice and all those things during ice region. So this is what model can do. So we use it eventually for prediction. As I told you, the importance of mathematical modeling is they are more reliable than ordinary intuition. Mathematical model also simplify analysis. Good model is economical because it saves cost when you are operating with models rather than operating with experiments directly. Model can be used for one purpose, can also be used for different entire purpose. So this condition here is very, very important in modeling. That model must be general, just like Professor Trump was talking about machine learning, uh, tools. So predictive algorithm tools, they must have wider utility purpose. That is why you have, for example, a model you can use in epidemiology. You can still use the same model also in studying crime, like Professor Emo discussed yesterday. The same model can also be used to study corruption because all of them share the same pattern one way or the other. So model, a very good model must have general utility. It will not be specific to that problem you have to use it for that purpose for it to be a good model. Then when you design a model, there are some things you must check to make sure that those models satisfy. Some of these things you check here is almost similar to when you have a data and you use machine learning to train the data, and then you come out with what we call, what we refer to data modeling. So you come out with result. You must check whether what you have is good enough. So the first thing you must do is to validate the model. And that simply means you test the model and use empirical data to verify whether the result obtained from the model actually reflect the reality. That's why under data modeling, you have to split the data into two forms. The first data, you use it for testing for training the data. Then the second one, you use it for testing. So, and those, you have to separate them and do some testing. So you must validate the model via use of data. That is empirical data. Like in mathematical modeling, because of the fact that usually there are no too many data to use. You understand? So what we just do is to first of all test the initial condition, the boundary condition, to see whether it satisfies it, and to see to what extent or the range of values for which that model may be valid. Because some models, they are only valid in a very short interval, and some others are valid for a large interval. So you have to test all those sort of things for you to really know that, yes, if the model satisfies those initial conditions, you know that the models is very good. You need to do what we call sensitivity analysis on the model. This simply means that the result from the model from one scenario should also be applicable in another scenario. If the model is just only applicable to one scenario, then it is not a very good model. Just as I told you, the model must have larger utility value. Next, we must compare the outputs to the data available. So if the model can be used for prediction, then it means that from the data you have, you must check that the output coming for the model actually is close to what you have in the data. Then the model must be sensitive to various changes. So you see how sensitive the model is to various changes. And this property is general for all models, irrespective of which area or whatever problem you are solving. The difference between the result you obtain from the model and the real data must be very small. In other words, the error that you must do error analysis of the model you are using. like Professor Trump was talking about, you have to do analysis, you know, you have to check what we use. We have what is called error estimation. And some of those facilities, they come from statistical estimators, which you have to use to test, most especially when you are dealing with simulation. Simulation itself is more about applying machine learning algorithms, and you apply it on the data. So you must check some things to make sure that, yes, the error produced out of it is least. If, for example, you design a missile and then you plot the trajectory, and the missile, for example, is supposed to bomb Lagos, God forbid, and then your model, you send the missile and it goes and bomb Ghana, you know there will be problem. So we must make sure that there is accuracy in the results, so that at the end of the day, the error in it, that is from the output you are expected and from the data you have, the error must be as small as possible. So then you must check you must know the weakness of the model. What are the conditions that limit the performance of the model? So that you can know that this model can only be applicable within certain, under certain conditions, and those are the strengths. And anything outside that condition, then the model cannot be applicable. So we must do some analysis, and that is where all those mathematical methods have to come into being to make sure that you are able to evaluate the performance of the model. Next, you must know the strength of the model, investigate conditions for which model perform very well, and know under what condition the model does not perform well. Now, simulation. Simulation can be said to be imitation of event prescribed in the stochastic or random experiment. Like, for example, Monte Carlo simulation, which was developed by von Neumann when he was studying problem of nuclear shield during the Second World War around 1945. So he was trying to look at the ruthless game which is played in the city of Monte Carlo, and then he now tried to see how real life problem can be replaced by stochastic random experiment. So what we normally use is to make use of random number generator, and those can be done from different ways in the statistics. So we have different methods, different algorithms which you can generate random number. So that you can replace real life experiments by using something like averaging that experiment over real life. And that Monte Carlo is very, very applicable in the area of simulation. We have it in theoretical physics, where you can talk about behavior of particles, which you use it. Even in mathematics of finance, we use Monte Carlo simulation, because when we formulate financial problem and we model it, and we want to use it for prediction, one of the easiest way of doing it is to design a Monte Carlo experiment for it, and then use data to simulate it. So experiments that are influenced by random events, because in real life, everything that is in real life contains a lot of uncertainty. So for that reason, we will have to simulate the problem using random experiment or from stochastic perspective. But sometimes when we are dealing with values that are very large, that are big enough, like population of a place, population of environment, we use something like deterministic model. That means we can determine the value using from the initial data, we can predict. So we determine, so we use deterministic model. But when you are dealing with things that have variations, small variation, things that have uncertainty, the best way of modeling them is to use stochastic or random variable. So those sort type of modeling is what we call stochastic modeling. Then we have what is called numerical simulation. Simulation, in essence, simply means you have a model and you want to use computer environment with the data to solve it. So that's simply simulation. So people that are using machine learning algorithm, what they are doing from mathematics perspective is simulation. But people that are in computer science, they may have something a little bit different from the perspective of mathematics. All we know in mathematics, it simply means that simulation means application of mathematics in a computer environment. So because computer has helped us to process data, because in model, when you are calibrating model, you use data to calibrate it. And for you to do prediction with very large data, you need computer. So that's where simulation comes in. Numerical simulation simply means providing numerical solution to models. You know, in mathematics, there are several different methods for different type of problem you can solve. But when it comes to the theoretical solution or analytic solution to problem, many of them are intractable because of the non-linearity that is there in nature. Because of the non-linearity of process in nature, there is no way you can have a method that can provide general solution. Even the best non-linear analysts sometimes may find it difficult to provide analytic solution to a problem. And that is the reason why we need approximate solution to problem. And that's what midwife numerical analysis. So we can have a problem that is formulated or a model that is formulated in differential equation, in control theory, in optimization, which we need the solution, and we cannot get theoretical solution direct. So we have to resort to looking for approximate solution. And that is what is called numerical solution. So now when we are now implementing numerical solution in a computer environment with a lot of data, that's what is called numerical simulation. So that we are doing numerical simulation. So simulation has many steps. The first sort of step we consider here is talking about modeling. The second set is talking about how do you process data to validate the model, so that to make sure that the model is accurate, and this is what is called validation. The other aspect here is talking about calibration. Calibration simply means the model comes with a lot of parameters, a lot of constants. So you have to determine those constants using methods. Those methods usually, they normally come from statistics for us to use it, or they come from our knowledge of machine learning. So to be able to find the data, like for example, using time series analysis in statistics, for example, using linear regression, using neural network model, for example, and using other things in control theory and so on, to be able to estimate from the data, to be able to estimate the parameter. So the parameter that goes into the model, you need to estimate them. And usually you estimate them from data, or sometimes you estimate them from boundary condition and other sort of stuff before you can begin to apply the model for simulation purpose. In developing good mathematical model, there are some skills you need to have. This basic skill, which other area or whatever problem you are solving, some of these things must be very there for you to have a very good model. The first thing is that you must ability to reason very well, to reason about the problem before you can begin to abstract it into mathematical form. The other aspect is you must understand the problem. The problem you want to solve, you must understand. And you must understand that when you formulate the model, which aspect or which area of mathematics you want the problem to fall into. For example, a problem can be formulated, like for example, we are talking about disease, for example. One person can formulate the mathematical problem or model using differential equation, for example. Another person who is more conversant in area of operation research can also formulate the problem from operation research perspective, or another can formulate it from statistical perspective. And that is, from statistical perspective, means that you want to solve the problem from use of data perspective. That's where machine learning comes into play. Another person can formulate the problem using concept of nonlinear algebra or linear algebra. So you must understand it, because once you put it in mathematical form, the results or the model you have, you should be able to use your knowledge of mathematical theory to be able to solve it. If not so, the model will become as useless as anything. So that understanding becomes very problem. Then there must be problem solving skill. Your ability to solve the problem must be there. Your ability to predict the problem. Predict the solution to the problem. Your ability to interpret the result, because when you solve it mathematically, you should be able to interpret. That is feedback, go back to the real world and interpret the result from the real life perspective. You must have what is called fluency. Your ability to use the method, the techniques, and all that to be able to solve it and to reason very well. Now, in order for us to see how we can apply mathematical modeling, we want to zero it down, for example, in the area of disease, for example. And then we model at different spatial level. Let's consider it from disease perspective, for example. There are several researches that are pioneer to understand temporal spatial dynamics of disease. For example, when I talk about temporal spatial, I'm talking about we want to study how disease grow with time. That is tempo, dealing with time. How does it spread with time? And how does it spread across an environment, for example? So you talk about the spatial nature, the dynamics of a disease. And in order to understand that, there are a lot of things we need to do. We must formulate, we must look at the disease. How does the disease itself is formed? Like, for example, the disease today that is reigning is COVID-19, for example. How does it form? Then when it is formed, how does it enter a human being? And when it enters, how does it grow inside a human being? These are some of the things you have to look at. So some of the things have to do with the growth with respect to time, and within the organism, how does it spread around within it? So those that, and how does the disease propagate maybe within a person? So why are we talking about various partial time scale? For example, COVID, every day, Center for Disease Control is reporting how the disease is growing all over the world, from one country to another. Then we can also look at the disease, for example, if it's planted in one human being, how does it grow in the bloodstream of the person? How does it grow in the tissue of the person? How does the disease grow also in the system or the organ of the person. So these are different time scale which we can, if we discretize the system of the person, maybe this the organ, the tissue, and all those things, because it represents some scale that is in discrete form and all those sort of things. So we want to study it at different time scale. But many investigations are conducted at atomic and subatomic level. You agree with me that most of the diseases we normally study, we usually study it at what do they call it? At some are at micro level. At that micro level, that is the smallest possible it level within the organism. Maybe within at the cell level, we study that. And most researches, modeling that people do, very few people are doing research in that direction. And it at atomic and as subatomic level, that is where the true solution to the problems lie. For example, somebody that have cancer, if you want to treat it, you need to study the cancer cell itself. How does it grow? So within the atomic level, and to know how does the drug will work at that level. If you are able to get the effective drug that work at that level, that will provide the cure to the problem. Or if, like in the case of vaccine, at that level, what are the things that the vaccine must contain so that it will be very effective? But at this level, that's where the solution lies. But very few people do research at that level. That is the atomic and subatomic level. But when you are talking about within the environment, for example, a population of COVID in Lagos is so. Population of COVID in Abuja is this. So we are talking about within environment. That's at macro level. A lot of research have been done. And every day, majority of the researchers that are working in that area, there are many. And the real problem is at this atomic and subatomic level. And when you are talking about solution, cure, that is at the level where research needs to be done at that level. Then we also have, for example, from genetic mutation point of view, for example, a tumor. When we talk about tumor, we are talking about when cell grow beyond its normal proportion. So there are many results or many scientific explanations to explain why tumor happen. For example, many scientists are saying as a result of genetic mutation, when the DNA copy is corrupted and you have a mismatch of gene. So that is happening at the atomic level and subatomic level. So we have to look at the gene and see what happened at that level. Is it true that there is mismatch? For example, we have COVID-19. There are about 3 or 30 variant forms of COVID-19. So we have to look at it at that level. What is causing variation within them? And this is where our knowledge of stochastic process come in, and whether we can simulate it using knowledge of Markov chain at that level. And we have to check whether the present state of the gene does not have, the past does not influence it. As you have Brownian process, we know that Brownian process, they lack memory. And many of such type of things, we need to look at it, and we have to come out with models that can actually represent those things and to see how best we can use it to predict and to study the disease. There are other things we can study at that level. For example, when the disease or the pathogen is planted on somebody, what are the receptors that receive them? What are the properties of the receptors? Which drugs can we use to inhibit it at that level? Or because these cells, they replicate and they need enzymes that will allow them to replicate. And what enzyme can we block or inhibit to make sure that that cell did not replicate. And this is where the drugs, the vaccines becomes very, very important. So we need to do that. So we have to study the dynamics of disease at the cell level, at the tissue level, and the whole body. So when we come to whole body, we want to know how the body system, how does it affect the body system or the organs. That's what in medicine we call physiology of the disease. So cancer has been one of the major problems in the world. You agree with me? It's one of the most killer disease, even in Nigeria. Many people that die from cancer are by far more than those people that die from even COVID-19. Last year, I lost my immediate senior brother with cancer. He has carcinoma of the liver. That is liver cirrhosis, which eventually grew to become a cancer. So cancer is a major killer disease, and many work are being done. Many researchers are looking for the drugs that can take care of it. Many of them are doing research to come up with vaccine that will be potent against it. So the dynamic behavior of cancer cell is a very complex and is stochastic in nature. And to combat disease, it needs thorough understanding of the formation of the cancer within the body, and then the spread of the disease within the blood circulation and the lump. So we have two types of cancer or tumor. We have benign and malignant one. Benign is when it is localized. Tumor, it simply means when a cell grows beyond the normal proportion. And such cell can be local in nature. Maybe it's only in one place. For example, somebody have breast cancer, it's localized, like a lump in the breast of the person. So we call it tumor. And at that level, medical experts can easily handle that. Maybe through chemotherapy, using some drugs, or through some radiation, burning off the cell at that level. Then you have a situation wherein the cancer can spread around the body. And when it spread, we call it, the process of spreading around the body is what is called metastasis, when it spread around the body. And then it can spread to the bloodstream, it can spread to the lymphatic cells, and all those sort of things. So scientists have been employing what we call multi-agent modeling techniques to stimulate cancer model. The essence of simulation actually is to explore what are the tools for better understanding of the complexity that surround cancer proliferation and the strategies to combat it and possible treatment options. There are different treatment options. So using radiation therapy, burning up of the cancer, then you can use chemotherapy through the use of drugs. And many people are still exploring different ways. But all you need to do is that you need to understand how does it proliferate, how does it spread around the body, and which part of the body, when it spread, that you can target to be able to control the spread of the disease in the body. And then what are the treatment options you can choose. And this is where mathematical modeling becomes very, very important. Because for you to know the best treatment option, you have to subject it to some operational research tests, some optimization to see which one will give you the optimal control strategy or optimal solution to the problem. And there are other things, but all of these things must have to be based on the available data that you have. But you can have to design models and subject them to different kind of tests. The dynamics of cancer evolution from subcellular to cellular level up to tissue level and down to the whole body using multi-agents and at various time scales, that is as it evolves with time and then within the tubes within the body, which you can look at it as it go around, as it spread around the body. We have different kind of mathematical models that are applicable. So tissue formation and simulation, we have a cancer cell that comes as a result of carcinogenic substance. What do they call carcinogenic? Things, some pollutant, for example. When I use the word pollutant, I'm talking about anything that's capable of entering into the system, that is foreign to the system, that can cause some disruption of the process. Like many people, for example, they use different kind of creams, and some of the creams contains some heavy metals that is capable of causing this body system to have tumor. So some type of thing are carcinogenic. And immediately when this thing enters the body normally deploys the antibodies, or the body immune system, different type of cell will be mobilized to attack the cells. And if it attacks it, it leads to a process we call angiogenesis. That means all the dead cells, it gather them together and then put them somewhere in the body. Like for example, you see somebody having boils in the body. So when the immune cells attack that disease and kill it off, they gather them and they come up in form of boils where they will gather, and later when it bursts, you will be seeing pus and other things. But sometimes the disease do overwhelm the immune system, and then that will now allow the cell to keep on differentiating and then formation of tumor within the body. And for us to be able to design a modeling tools, because I tell you, simulation tools help us to monitor the growth of the thing. We have to design a simulation experiment. That means we first of all come up with model and then see how we can write some computer programs which will allow us to test how the model, how this cell is growing within the body. So through simulation experiment. So we have that. So the normal cell become carcinogenic. So we have computational engine here. That is the algorithm we are going to use to power the simulation from the data, and then begin to come out with outputs to see what is happening. How does it grow? If we introduce drugs into the body, or if we introduce any method into the body, we see whether the population is retarded, or have we really eliminate the disease, or the thing is growing, and all those sort of things. So drugs and vaccine and effects. To study the effect of drugs or a vaccine, we need to study the behavior of that vaccine at the subatomic level. That is within the cell, within the blood vessels and other things, to see how they behave. We can use both deterministic and stochastic model. Stochastic model is sometimes very effective when we are looking at it from genetic point of view. Also, if we know that the variation is very small, we can come out with stochastic process. This is where you have model, like in case of sickle cell, when you have been talking about using Markov process, Markov chain, and all those sort of things to study it at that level. This is where you have to deploy some stochastic process. If you have data at that level, you can deploy some statistical process, like using Gauge model and some time series analysis at that level. You can use some quality control model at that level to study that. You can also come up with some deterministic model. Some of the model I will see, they come from differential equation. Some of them are ordinary differential equation. Some of them are from partial differential equation. And partial differential equation is very, very useful here. We will see some of them. Like, for example, you come out with different type of partial differential equations. Some of them are parabolic in nature. Some are elliptic in nature. And you will begin to think of how you can solve them. This is area where we talk about the use of multi-domain physics simulation. So you use multi-domain. That means the space, you have to discretize it and then use the knowledge of finite element analysis to analyze it, or finite volume analysis to analyze it. And we have so many software that contains those facilities. And the engineers normally make use of that. Like, for example, in Math Lab, we have what is called PDF tools, which you can use to model sort type of problem within that area. You know, you discretize the environment. For example, if you are interested in studying cancer, for example, of the lungs, and you are able to get the geometry of the lungs where the thing happens. So using finite element analysis or finite volume analysis, you can analyze it. And those type of things, there are software that you can use. Like, for example, Kumson uses those type of things because it uses the knowledge of multi-domain analysis to study that. And so many engineering software facility can use that. In Maple, you have to, if you discretize the environment, you need to write Maple code to be able to get all the functions that describe the multi-domain. And then you can begin to model it and see what happened at that level. So I was thinking that the laptop that I have, Math Lab, has problem. So I'm unable to use it because the sound system is not there, and we try to install, not working. I could have demonstrated in that area. But the other area, we are going to use Maple. Maybe but tomorrow, when I'm looking at modeling in the marine environment, we'll demonstrate some of them where you can do it. You can also study the physiology of the effect of drugs. Physiology simply means how does it work in the body, the overall, how does it work? That of drug or vaccine. So in that case, we talk about systemic model. So you are modeling the system as a whole. And in that case, we'll be talking about use of compartmentalization model. Like Professor Emu Ibrahim was talking about, for example, you have to trace it. For example, if somebody inhaled COVID, how does it go into the nose? How does it go into the lungs? And all those sort of things. So there are compartments, different compartments you have to model to be able to get a total overview of how that COVID actually works in the body. So when it gets to the lungs, you even go into the alveolar, then you are going to the subatomic level to see how does it affect the cells. And if you have to have drugs at that level, what must you do to be able to get effective drug at that level? That is at the subatomic level or the atomic level. Now, the most challenging disease today, first on the list is COVID-19. So far, even in the United States of America, more than 6 million people have COVID-19. And the whole of Europe, many are affected. Like UK has gone into another round of lockdown. And in America alone, more than 250,000 people are infected. And globally, over 8 million people have COVID. Although there are a lot of vaccines that are undergoing clinical trial, like Pfizer in US, they have come up with vaccine that have undergo the test stage of clinical trial, and they have found that it is about 95% effective. Then in UK, Cambridge University have tested their own vaccine, is about 70 or 75% effective. China is testing its own vaccine in Brazil, but they have not told us what is the efficacy of the drug so far. Then the second one is cancer itself. This one has killed so many people and is keep on killing people. So people need to do research to be able to come up with results. But one of the most dangerous one now is eczema disease. Eczema disease, which is affecting a lot of old people. And this disease, so far, there are no potent drugs for it. And so far, research in that area is limited. But we employ our young researchers to look at these areas, to come up with research. But in this area, there is a lot of data that is available. I remember Professor Trump once last year or thereabouts sent some data to me in that area, in which case we can model the data using machine learning algorithm and do some prediction. Or possibly if there are some models we can use that has to do with studying the nerve system and so many kind of things. But I know that all these diseases, they have to do with knowledge of invasion of the environment by some pollutants, one way or the other. But how do we identify what are the pollutants? What happened into the environment? So that scientists are seeking for most efficient drugs or vaccine to combat these diseases, these diseases, and mathematical modeling and simulation can be pilot method to getting that. Mathematical modeling of tumor and the efficiency help clinical to design treatment and regimen options and all those sort of things. So we use different kind of things like simple Brownian motion. We have other things like reaction diffusion model, and then you study the pattern of formation of cancer using what is called epiaxial models, and then using pattern recognition model that has to do with fractals, because if you model cancer, we can use some fractals to describe the model. So we have to use knowledge of our fractal geometry to be able to model some of these things. So we need to use some geometrical models, and many Nigerian researchers are not doing modeling on geometrical models. So geometrical modeling is very good in this area, able to model other things. And I told you also you can use multi-physics domain, where you use finite element method, finite volume analysis to do the analysis. So I'm encouraging most of our students they should work on cancer using PDE, not only ODE, to explore those areas. And then other things are use of quantitative and qualitative analysis. Now, let us look at some models. Some of them are phenomenological equations that are used to study the growth of cells or growth of disease within a cell, and how does the various diseases react to presence of drug or chemical, or what you call chemostasis, or how do they react to different kind of taxes within the cell. Because for you to find the best drugs, for you to find the most potent vaccine, you need to know about effect of the dynamics of the disease and how are they responding to the presence of chemical, or what you call chemostatics effects. The first and the most simple form of model which was used to study cancer, and so many, even in telecommunication, we are still using this model. Because I told you earlier that the best model must usually have general utility. So it's called Gampes model, which is represented by this. We have other models that are being used. Although this model, when they designed them, they were used on cell to study something. But I can still tell you that this model, because I told you a good model must have utility, they are still useful to study different kind of disease in the body. They are not limited to the original disease, which McKendrick and Foster used, but you can still use them to study the behavior of diseases, behavior of cancer, like this first McKendrick process here. When you are studying the population of cells that are structured according to time and age, the age structure. Like we have COVID-19. The COVID-19 is structured according to age. Most people that are dying more of COVID-19, they are those people that are age of 60 and above. So this model, you can use it in cancer. Population of people that have cancer usually are elderly more than the small children, although there are some small children that also have cancer. So age becomes very important. We can study the dynamics of cancer structure according to age, and structure instead of age here, structure according to some property or condition within the system. So this model is very, very important in this direction. So we consider this PDE to study, and it also have other utilities, as I told you, even in marine environment and other places. I remember there was one of the paper, we look at it, the effect of chemical within the marine environment, so which this model become very useful. And yesterday I saw somebody just use this model on COVID-19, this Gampes model, where you want to study when the curve of the COVID-19 will flatten, and this can use it to describe the dynamics of COVID-19. And we still find that there are other models like hyperlogistic model. In my book on ordinary differential equation with maple application, we come out with some result, and you can use it also for COVID-19. And you can use that to design algorithm using data. I have told one of my colleagues to see, because if you look at the curve of COVID-19, it's that logistic, hyperlogistic model can describe it effectively. So we have something like this. So we also have Kep-Fisher model, this model here, which you can use to study it. And then this is the diffusion model. So there are many models, those reaction diffusion models, which you can use for studying cancer. We can use reaction diffusion model here if you are localizing cancer, for example, into a local environment. So the geometry of that environment, we can use finite element analysis within that environment with this model to study how does the cancer cells spread around that environment. Maybe within the liver, for example, if you have multi-domain structure of the liver, for example, and then you can use finite element analysis, finite volume analysis with this model to study how the cancer grows within the liver or any other organ within the body, maybe pancreas and so many other areas, using finite element method or finite volume element analysis. This is the area very few people are working, because you have to deal with a lot of discretization of big data, which you need to analyze. You need to use something like Galecki method and other things to study it and to be able to see it. So this type of models, they are very, very, very useful. And there are other new ones that have come into it, maybe part of form of this, when you have other factors that are coming in, some control factor here that comes in, maybe as a result of presence of pollutants within the system, or the control here, which may be as a result of drugs, as a result of use of supplement and other things. If you introduce a function in which model the drugs or which model the complement. So this parameter here, for you to determine it, you have to use data. So here we have a case where R here is a constant. In some problem, we can consider a case where this R is not a constant, which may be a function of X or function of N. So how do you estimate that parameter? This is where machine learning algorithms and others can come in, or statistical method for you to estimate the parameters. Is it that parameter here? You can use some statistical model. The simplest one, just like Professor Trott talked, is to use regression method, linear regression method. You can also use GATCH method. You can also use some things, if it is hard to do with this parameter, has something to do with time. You can use time series analysis to evaluate it. This is the maximum, what do they call it? The maximum carriage capacity, if we can predict it. And this parameter also, we can estimate them. The diffusion from experiment, you get that. This also from experiment. And we can also estimate this parameter also using inverse process or inverse method. There are many methods or models that you use inverse problem. I can see that in Nigeria, very few people are working on inverse problem. So that from inverse problem, we can determine this, to be able to calibrate this model. So when we calibrate it before we go into simulation. Several models are used to investigate chemotherapy that are induced by apostasis. What do you mean by apostasis? Apostasis simply means that is the killing of cells, and then maybe killing of cells by the immune cell system, and then gather them together in a spot, as I explained. And then we have different kind of drugs. The process of angiogenesis, it simply means formation of blood vessels within the system. For example, cancer is connected to the system of the patient, and there are some blood cells, blood vessels from the cancer that drain nutrients from the patients and also oxygen from the patient. So one way of controlling cancer is to cut off that blood vessels so that the nutrient, the blood, the oxygen will be cut off. And so those drugs that have that property is what we call genetic drugs. And those vaccines that will be developed should be able to have this type of property. So apostasis, as I told you, is to remove cells, dead cells, during the process of development and also during the process of elimination. So therefore, when we model a cancer cell, we must think about, in the parameter, what must we do to be able to see that these cells of the disease, maybe cancer, maybe COVID, are eliminated through the process of apoptosis. So some of the parameters that goes into the model should be able to help us to achieve that. And other investigation and interaction of cancer with the immune system. So we talk about immune system like cytokine, microphage, and we also use other things like interferon and adapting immune cells like B lymphotic cells, which are within the system. Then we have other drugs like immune boosters like injection of cytokine. Later, we'll discover that when we are going to talk about introduction of drugs into model, so we'll begin to study the model in relations to this drug function, which we can get by introducing some of these things to boost the immune system so that the body system can easily fight off the disease, even in the case of cancer. Now, let us consider this cancer cell. So this cancer cell can be modeled by this equation. So this G of N can be modeled using different kind of representation. The very simple one can be just a simple linear equation, for example. Maybe we represent this as a function of straight line, which is a simple model. Just like here, we have this, which is simple. And then here are the immune system, different type of immune system that are in the body. Different type, like CD4 cell, C8 plus, and different type of the body, which are mobilized into the system to fight off the cancer cell or the carcinoma. And then here, this aspect takes care of the drugs. And not that alone, it takes care of the metabolism that takes part in the cell. Metabolism is talking about ability to break down, ability to build, which is called anabolism, and ability to break down, which is the catabolism. And for those things to happen, oxygen is very, very important within the cell. So therefore, we must find a way of, in order to control the growth of the cells, there should be a way of controlling the effect of oxygen within the cell. I talked about earlier about anti-genetic drugs, wherein it will cut off the blood cells or the blood vessels connecting the cancer cell to the system of the patients. So drugs that can cut off and make sure that the cancer cell did not develop those blood vessels that connect to. So and when the blood vessels are not connected, so the oxygen that is available in the bloodstream of the patient will not be getting into the cancer cell. As a result, the cancer cell naturally will die off. So these are some of the things. Then we also have other factors. Later, we are going to consider the effect of drugs or vaccine that goes into the model. And then we'll now study how does the cancer cell grow, how does the immune system grow in the presence of cancer cell, and which other method or treatment method we can use to retard the growth of the cancer cell. Some of them, chemotherapy, as I told you, if we cut off the blood vessels connecting the cells, so two chemotherapy way, or probably two radiation to cut it off. So these are some of the things. And this is the population of the cancer cells present at a particular time. And this is the number of immune cells of various types that are present at that time. And this M here is a genetic factor that determines different type of family. How are they susceptible to cancer? Some family, they are not all that susceptible to cancer. But some family, on their genetic makeup, they are susceptible. So this takes care of the genetic factor within the cancer cell. So we can study if, for example, the cancer is taking some quadratic growth, where GN here is modeled by this, and this factor is 1. So we have a model like this. So this type of tumor cells is localized to a point. As I told you earlier, for example, a tumor that is localized like a lump in the breast of a girl, or a tumor in the pancreas that is just coming up, so localize that. But sometimes, after some time, the tumor can spread along the blood vessels and the lymphatic cell. So this case, we call it benign situation, or what we call malignant situation. So when we say cancer is malignant, that means it has spread around the body. And in that case, usually patients that have that situation, they have limited chances of surviving because it has spread like wildfire. How are you going to control it? But if it is localized to a point, when you talk about benign case, so we can easily take care of it, whether use of chemotherapy drugs to kill off the cell or radiation and all that. But when it has spread around the body, so you have malignant case. But this is another case of benign case when that G is obeying some logistic equations. This G of N can also take Gomper's representation. And then we go on, we come on with that. We can now have another case in the case of malignant one. When metastasis have taken place, what do we mean by metastasis? It means that the local tumor has started spreading around the body. It spread to the blood vessels, spread to the lymphatic cells, and then it has go around the body. So how do we control that? We need to do research. First, which other things must be introduced? Here, this factor here, we need to have some data about the spread, clinical data, and then we have to model the data to be able to get the function here that describe how drugs was working from clinical data. And this other data too, they are this parameter, they have to get them to clinical data to get them. Some of this must be from clinical data. And that means that we have to work with the medical experts to get clinical data. Another thing again is that if we can able to solve this model equation under that certain condition, that will help us to get, we can use it to formulate the algorithm for modeling of data. But in most cases, it's generally very difficult to do that. But you can have a simple case, for example. If you have like Gomper's model that we saw earlier. Gomper's model is a solution that arrives from a simple differential equation. And because it's the solution of simple differential equation, so we can use, we can tame that model equation with data to be able to get an equation which you can use to predict the growth. The same way, this year, we are able to solve this. We solve the equation using some transformation. It's not here. Using some transformation and from clinical data, when we study the behavior of the rate of production of the immune cells, we input them. Then this equation just simply became an equation in which all the parameters are inside, so we can easily solve it and begin to study the behavior of the cancer cell as well as the immune system within the system. So this parameter here, we need data, that is use of our statistics, different modeling statistics to get all these parameters, to estimate the parameter. So when we put the parameter in, we can easily solve the equation. Solving it analytically, but sometimes solving it analytically, particularly for this problem, is very intractable. So that is the reason why we have to resort to the use of numerical simulation. And in Maple, for example, there are different solvers that are present inside. I think the simpler one, which we know that is very accurate, is Runge-Kutta fourth and fifth method. It has desirable stability property, and it is consistent that so we can use it. But sometimes some of the model, like in this particular case, we found that the model is not stiff. But if it is stiff, we still have to use a solver that takes care of the C system. Or we can as well, from this, use numerical methods. Like Professor Numaya and others, they have developed so many kind of solver method or solver which you can deploy, writing some computer code which you deploy, and then it will give you the result. My book, which was that was sponsored by TED Fund, I'm sure many people have it, that was talking about ordinary differential equation using Maple. In that book, we consider what is called symbolic solution. That means analytic solution. We can deploy it. But if you write Maple code, you discover that the solution analytically will be very frightening. I recall, to provide the analytic solution, I discovered that one solution can even, if you have to use computer printout, it will take about 15 pages of computer printout. So which means the solution becomes useless or meaningless. So for that reason, it's better to use numerical methods. So I have now introduced numerical methods into the revised version that will be coming out very soon. So Bentham in United Arab Emirates have agreed to publish it. So we have introduced numerical one. So we wrote so many Maple code to generate solution to problem like this inside. And then other things in mathematics is you can begin to study the stability analysis of some of this. First, other things you normally do is to determine the equilibrium point for this model. And what you do is just equate the right hand side of the equation to be equal to 0 and then solve for n and r. So in Maple, there are code you can use which will help you to generate it. Here, this is, in this particular problem, is a 4-dimensional problem. If you have to sit down and solve it analytically, you all agree with me, it will be very difficult to do that. And you can even have a situation wherein to get a comprehensive model, there are other cells that must come into being. So, and the model will be very bulky. It may even go as far as a 16 by 16 matrix problem. So which if you have to sit down to say you do computation, it's not going to be easy. Except if you have to scale the model down, discover what are the essential part of the model or the variable that are very useful, you scale the model down, and then you do the study. Is that okay? So in differential equation, we'll be talking about comparison system. So we'll come out with a comparison system, which is somehow smaller in nature compared to this. But then the behavior of this system here is perfectly represents the whole system. That the daughter system here perfectly represents the mother system or the parent system. So in that, and then so we have the general situation here. Here, I told you one of the easier way of to control any disease is to see that you cut off that disease from getting supply of oxygen, because oxygen is very, very important. But at the same time, if you try to cut off oxygen from the disease, and oxygen is cut off from the normal cell, it can also lead to death. because oxygen is also needed in the body for metabolic activities. So one way of control is in the model is presence of oxygen. And I told you that they have drugs that can do that, but then it has to be targeted. It must be targeted so that it will not affect the normal cells. The other factor again is the use of drugs or vaccine, use of supplements, which you have to introduce to be able to reduce the effect of the malignancy, which is this factor here that goes into the model. Then there are other factors here. This is that the immune cells. There are some things you can also introduce to enhance the performance of the immune cells so that they can fight off. Some of them come into form of drugs and supplements. The immune system tends to be boosted if you introduce something like vitamin C, which will make the immune system to grow very well. And there are some supplements and other things. There are some drugs you can introduce. So collectively, so we have to study the dynamics of the cancer cell itself, study the dynamics of the immune cells, and then the effect of the drugs or vaccine, and also think of which way can we use to cut off the cancer from getting nutrients and supply. So this parameter here should be able to estimate all those things. But you know, it's easier for you to come out with model. But another thing is that the medical doctors or the biomedical engineers are supposed to think of how can they achieve that. We can achieve that, some of them through drugs. Some of them, there is a need to design some equipment that will be able to achieve that. Maybe such equipment, they will introduce it to the patient, and the equipment should be able to extract oxygen within the surrounding of the cell. So biomedical engineers, they have to think of how do you achieve some of these things. So this model here is designed from Fokker-Planck equation, and this one here is from Hill's model. We are able to come out with this so that to study the behavior of oxygen within the blood system. And this actually model was from one of our models when we are studying sickle cell anemia. We discovered that the sickle cell anemia model, one of the basic problems the sickle cell patient used to have is the oxygen depreciation because of the sickle nature of their blood. So in order to boost it up, they have to introduce drugs that will boost the retentivity of oxygen. And this is where these parameters they are coming. We can also do the same. So we are modeling the behavior of the cancer cell in the presence of drugs or vaccine, and also other means to checkmate the presence of oxygen. And this model are coupled together. So it's a coupled together. So using our knowledge of chemical reaction and other things, we're able to come out with this model, which is coupled together to study the dynamics of the cancer cell in the body. So other things are sensitivity analysis. Sensitivity analysis become very, very important because we want to see how are the parameters the model is sensitive for parameter. You see, we mathematicians, we really like to see what will happen. But for example, in order to really test that model in a place like Nigeria, for example, it has become very difficult for you to test this type of the model design because there are no adequate data you can use to get some of these things. But in the case of growth rates and all those things, we can get them. In the case of parameter of how the immune cells grow or die, we can get those ones. But when it comes to here, when you introduce oxygen or reduce oxygen, it's difficult to have information. But people that are in developed countries, they have those data. So this type of model, to calibrate it, we need those data. So people like in US, other developed countries, they may have data for calibration, which can be used to fully test this model. But notwithstanding, that does not mean that the model cannot be useful, because those people that are over there, when they come across those type of models, because they have the data, they can also test it. We can also simulate this model through some things. In the paper, we are able to obtain some results, to be able to compute the value of n, to be able to compute the value of r. So when we get r now, that r can give us, we can use it to formulate algorithm, in which case anybody that is modeling the disease from the data, they can just use that directly to model it straight away. Since you have a formula that represents it, you can just use it to model the data directly. So instead of now coming out with the differential equation, but if we have solution, that is the model equation representing R, by solving this problem, we can use that same model equation, in taming the data. You use it to train data straight away. You use it to train data, and part of the data, you can use it to test the effectiveness of the model using that formula straight away. So sensitivity analysis is very important. We want to see, with respect to this parameter, does it affect the penetration of the cancer? Yes, positively. So when you increase that parameter, that means if you allow the cancer cell rate of growth to increase, then the population will increase. So therefore, if we have to make sure that the cancer did not grow, we must find a way of see how to depreciate this. Maybe through drugs, through whichever means. If it is medical equipment, we are able to fabricate that can enable this to be reduced, then that is good. Then this one is negative. So which means that the population of the cells reduces with respect to this, and so on, other factors there. These are the factors that influence it. This B, the growth. This other factor parameters influence the growth. This influence the growth. So therefore, for us to control the cancer, we must find a way of checking this parameter to either keep it under control so that the cancer cell will not grow. And that will involve, we have to think of how people can do that. It may be introduction of supplements for the person, those people that have it, or introducing special type of diets that will make sure that this parameter here, maintain positive. And so the same thing with the immune cells. The one that boosts immune system is this one, which is positive. This also. So in order to retain them, we must also make sure that we maintain them positive. Maybe through use of drugs that will boost them, or use of supplement that will boost them, or use of food that will boost them. Other things, normally, you are always interested in the model equation we have. What is the equilibrium equation? And I told you earlier, to find the equilibrium equation, all you need to do is to set the right-hand side of the equation to 0. And then you can use Maple code to generate it. For this particular problem, this is what you get at the equilibrium point. So that is the equilibrium point for this immune system depends on the drugs that you use. And it depends on all the parameter that comes from the oxygen and all that things. So you have to think of how they are able to maintain equilibrium level of immune system and all those sort of things. Because all these ones become zero, because after some time, when the cancer cell is growing, the immune system will be depreciating until some of them become zero at a particular time, or almost asymptotically tending to zero. So we have to introduce some things. So medical experts must introduce what they will do. So numerical simulation, I told you, is that look, this particular problem, we solve it with a Monte Carlo simulation. But this problem too, if we can translate this problem into what did they call it, a tensor form, isn't it? If we can translate it into tensor form, we can use finite element domain method, or what we call multi fixed domain method in engineering to solve it. And those one will be localized to a place. You have to study the geometry of the area. The major problem is how do you generate the grids at that point.
Prof, sir.
Yes.
Prof, we need to take questions, sir. So yes. Maybe if we just round up in the next 2 minutes, sir.
Okay.
So participants can ask you questions. And for participants, please, once it stops, please start sending your questions now. So when it stops, you start taking them one by one. We have around 25 minutes to go.
So this is area. So numerical simulation becomes very important. But then, for you to go to numerical simulation, you must always, first of all, understand the mathematics, able to solve the problem, or using qualitative property. Like for example, in mathematics, we mathematicians, we are interested in interaction of analysis, geometry, and then algebra. Like for example, when you are finding something like equilibrium points, you come up with some algebraic equation and you solve it using your knowledge of algebra. So you are moving from differential equation, which is analysis, to algebra. So the two must interact. Then after you get the result, geometry come into play. You have to draw this the structure. So all of them must interact in order to have a fine mathematics. Many people are saying that people that are in modeling, they are not serious mathematicians. That is not true. Because for you to be a modeler, you must have thorough knowledge of pure mathematics itself. You formulate differential equation. You must be able to know under what condition the model equation exists. So knowledge of existence and uniqueness, or whether the problem is well posed, which means the solution exists and is uniquely determined by initial conditions or initial data. You must have knowledge of that. You must have knowledge about stability. Is the problem stable? That means if you get solution and you perturb the problem, is it stable? You must be able to know if you are using numerical method, does the method converge? Under what condition is the method stable, astable, and all those sort of stuff in numerical analysis. So that knowledge must be there. And then you must be able to know when you obtain solution, is the solution actually representing what happened in the real life system, or what characteristics you observe in the simulation? Is it due to what happened to the model you are solving, or it is due to the method that you have used? Because if another person used different method, the characteristic may not be the same. So that means that the method you use, you must be confident that yes, that characteristics is not induced by the method. So you have to know the thorough knowledge about the method. That is thorough knowledge about numerical analysis itself, to be to know that whatever you come out of it is a true representation of what happened, and not because of the method you use that you are obtaining result that is not really reflecting what is happening in reality. So these are some of the things. And then you can also look at other things like bifurcation. The solution bifurcates. The solution is showing oscillation and so many kind of real life phenomena that people that are in pure mathematics will be studying. Other things like when you are having problem that has to do with optimization, you should to have thorough knowledge about theory of optimization so that whatever interpretation or the result you get will give you true representation of what happened in reality. So thank you. So these are the other aspect. We use energy method to control the presence of oxygen, and then from there we are able to find under what condition can you minimize the presence of oxygen. I told you there is angiogenic drugs that normally cut off the blood vessels that connect the victim to the tumor cells. So those drugs, how do you optimize way of cutting off the oxygen that gets to the tumor cell at the same time without affecting the patient? So we look at the mathematical equation, so we are able to use our knowledge of energy equation to be able to obtain that. So energy equation is just using the knowledge of energy to find simple criteria that will minimize energy. We are able to design energy equation, and then the thing boils to this equation, and we solve the equation, and then minimize the energy. And then these are the minimum possible energy the cell must get. So if you can able to get that, the minimum number of cells is this for it to cut off the oxygen. So it is left for people that are using drugs to be able to achieve this. Or if you have an equipment, medical equipment that can achieve that, fine. Thank you very much. So that's it.
Thank you very much, sir. Professor Yelami, that was a very good presentation, very comprehensive, sir. We'll start, please, because of bandwidth problems, I will suggest that you type in your questions for Prof to answer. We have about 20 or 15 minutes left, so please send your questions in. But before I hand over to Prof, I want to ask him a question. Prof, sir.
Yeah. Okay, sir, go ahead, sir.
Yes, do you think that people understand the spread of COVID-19? If you look at the way it has spread in America, and they say Americans say they have a good model. Do you think that model is accurate if they can predict the spread in America and they cannot predict the spread in Africa? That's my question, sir.
Okay, yeah, thank you very much. We have at National Mathematical Center, we have a research group called International Thematic Research Group. And this International Thematic Research Group involves some researchers from China, Pakistan, Egypt, and so many other countries came together. I'm glad to inform you that Mo Ibrahim is one of the group. And we have come up with a proposal which was submitted to us. So the proposal we are supposed to look at, and Professor Trump is also part of the group. I'm telling you. So we are working on that to be able to see how we can use it to study the dynamics of COVID in Africa as a case study based on the available data. We want to look at how does it spread and also do some research on best way of solving the problem clinically and then demographically from the data. On the area of data, deep learning algorithms and all those things will be formulated. So that is what we are working. Professor Trump is part of the group, and then Professor Mo Ibrahim is also part of the group. So thank you.
Thank you, sir.
Yeah. Any more questions?
You have questions for you on the chat, sir. Click on your chat button. You see the questions, sir. Click on your chat button. There are questions for you, sir. There's at the bottom.
I'm trying to.
Okay.
It's not showing.
If you click on the chat, you see it coming up.
Okay, I saw it before, but it's not popping up.
You've seen it, sir? Have you seen it?
No. It's not showing. Before it popped up, but I didn't see it again.
Can I read it out? Can I read them one by one?
Okay. Ask.
This is from Ephesus Fatumbi.
Okay.
In the absence of experimental data for validation of experimental data, can the model be validated using existing model? In the absence of
data, you see, this is where we mathematicians come in. You can be wondering why mathematicians, for example, will spend their time talking of stability and talking about existence, talking about that, talking about sensitivity to parameter, because we know that the number of data you can get may be limited. So, but for you to know whether you want to validate the model, you can check some simple other possible models that are simple. You use it to validate. Simple one. But then, that simple model should be a particular case of the general model, in which case, when you slot in one parameter, it reduces to that one. So, but that simple one too must have to be validated to be sure that it is correct. Is that okay? So that's the difference between we mathematicians and then people that are using machine learning algorithms. Their strengths lie in the data, but our strength lie in our ability to develop the model. And we know from our knowledge or applications of from mathematics, we are to investigate under certain conditions that thing will work. You understand? So we spend more time investigating under what condition this thing will work, under what condition it will work. We know that in as much as we are working within the realm of the condition that is that, then it will work. Because of there is no data to really check. But we know from the knowledge of our mathematics that under this condition, it will work. If, for example, you under condition, you find that the solutions are negative, and you are dealing with population, does it make sense? Can population be negative? It is impossible. If population go down, the lowest it can be is 0. And when it is 0, we know that there is extinction at that point. But population can never be 0. That's why you have to investigate condition for it to have positive solution. So that means that the model will be valid if the solutions are positive. You understand? Even though the data is not there, but from mathematics, we know that it will be valid if the solutions are positive, and it is invalid when the solutions are negative. Because you can't talk of population that is negative. You can only talk about population that is 0. 0 at that point is talking about extinction. For example, in a situation where population is persistent up to certain extent, then it will tend asymptotically towards 0. Sometimes it may not be 0, but it's asymptotically tending towards 0, but not negative. So that is that.
Well, in the absence, there are no more questions. So maybe I can still add one more question to my own question, sir.
Okay, sir.
In this COVID-19 simulation that you are working on, sir.
Yes.
If your model, for example, can determine why it's not spreading in Africa the way it's spreading in America, can that result work against us in future?
Yes.
What I'm trying to say is this. If, for example, you discover that, okay, weather and some other factors is inhibiting the spread of COVID-19 in Africa, if somebody wants to attack us in future and it does a virus that can survive in weather, hot weather, wouldn't that be against our interest?
But if we are able to understand the dynamics, it can also help us to prepare to fight it. Let me start you an example. In America, bulk of the people that are affected by COVID-19 are black people. In fact, black person is 4 times likely to be affected than a white person. So what is responsible? Because of the diets. So the immune system, it appears their own immune system is strong, or probably there is something within their blood system that can make them to survive it. So when we are modeling, we have to look at the genetic factor. That's one area, because there are some part of trends or variants of COVID. So we are looking at area of variancy among the COVID. And other factors, probably why Africans are not having. Let me explain to you. A typical Nigerian man, if you check our blood, all of us have traces of typhoid and malaria. Are you with me? So there
Yes,
is
sir.
no any Nigerian man or African without no malaria. And because we have been taking malaria drugs, so we have developed a lot of resistance to certain extent of malaria. But now they have discovered that the drugs that they are using for treatment of malaria, I asked one doctor when this thing happened, who worked with teaching hospital in Abuja here. The early drugs they used, they were experimenting on malaria drugs and also drugs for tuberculosis. You understand? So many people here, they are getting immune to it. So it means that if they use malaria drugs to treat the early stage of COVID and it works, so this is why most Africans, when they even have COVID, because we are susceptible to malaria treatment, so because we take malaria drugs, that's why majority are not being affected. But in US, for example, before the COVID, you can go around the whole US and test almost everybody. You may not find one person with malaria there. So in West, because their environment is very neat, they don't have mosquito and all those sort of things. So, but we are being beaten by mosquito every day. So that we are getting immune to it. That's why most of those diseases that easily affect them might not affect them also. So these are areas they need to do research to know why. But I believe that because, and not only that alone, our system is being affected by diseases, different kind of diseases. So for that reason, our immune response is increasing every day. You will see a Nigerian man, if he does not have malaria in the body, he will have typhoid. If he does not have typhoid, some of them will have yellow fever. They will have all those sort of things. So the immune system is being trained to fight off. And that is one of the reasons, I believe. And we cannot say again because of the weather also. Because we have to study the temperature of the environment and the environmental condition to see why COVID-19 can survive cannot survive in African environment compared to those other environments. So that may be the reason. But these are still subject to modeling and testing for us to be able to conclude that these are the things that are responsible.
One more question, sir.
Yeah.
How will you advise young people for a career in simulation? Most young people in computer science don't want to do simulation as a career option because they don't see any prospects in terms of financial prospects for them there. How will you advise any prospective PhD or student to take simulation as a career option?
That is the best job in the world today. If you go to big data we are talking about, big data is about simulation, is it not? You come out with model, which you get obtained from the training of your data, isn't it? And then you test the performance of the machine learning model. It's simulation you are doing, isn't it? And predictive analysts, they earn the highest salary in US because there is a lot of data, business data, that contains some information and they want somebody to come and unravel it. And what you are doing there is simulation as applied to data. Is that okay? Machine learning. So that is that. Also, in mathematics or finance, you have quantitative analysts in the US, in banks everywhere, who are working on financial modeling, and they earn the highest salary. I think why many people are running away, because it involves very high level of application of mathematics. You can imagine all those presentations Professor Trump was presenting, even though it has to be with data. Our knowledge of statistics here is just to do with small data. But now, when you are looking at it from computer science, you need to develop algorithms. And those algorithms, they come, some of them come from something like abstract algebra that most of our boys are running away. You are talking about fuzzy set, fuzzy logic. They are core mathematics that people run away. And those are the things that you use to design the algorithm, which will power the predictive, to power the algorithm that drive the data. And people who can use them, well, they are the richest people in the world today. You can imagine Amazon and Microsoft, all of them, they are going to companies that do with Google, cloud computing and all those things. Who are the people that will be driving cloud computing and all those things? Who are the people that will be designing neural network architecture? They are the people that are in simulation, and they are people that are thoroughly grounded in the theory of algorithm and implementation. So it has future more than any branch. So modeling, simulation has future. It depends on which area you specialize on. People that specialize on disease control. Let me start you an example. You have Shade Agostu, who was formerly in UNAP. She started her career in Lautech, and she did a PhD at University of Ilorin. I know Shade, we have invited her for many programs in National Mathematical Center on modeling. But now she's a modeling in US now, and she works in a university in the Department of Ecology. So that means she's applying her knowledge of modeling in ecology. And she has been performing very well in that place. So if you get your PhD, you can model very well. You can analyze data very well. The future is bright for you than any other person. And that is really the modern computer science are those areas now. That's machine learning or data analysis, big data analysis, and artificial intelligence. That's modern computer. So, and in artificial intelligence, you have to design algorithm. You have to design random number generators who generate random number which you are going to use for experiment. And for you to design them, your knowledge of algebra must be very good. Your knowledge of statistics must be very excellent. That is why Professor Trump was mentioning it over. So they need to take it serious, because that is the future of the world.